Okay, we're live now. Hello, everyone, and welcome back to the DoraHacks Space Technology Workshop Series. My name is James, and today's topic is applying the NASA systems engineering process to a space project. So before I hand over to our guest, I'll just give a bit of background on DoraHacks for those of you who haven't tuned in before. DoraHacks is a leading global hackathon organizer and developer incentive platform focused on various areas of technology, mainly blockchain, space technology, and quantum computing. So we're really keen to support innovation in those areas. And we have a number of initiatives at the moment aimed to foster innovation in the space technology field. So we'll have links to all of these grants and initiatives in the comments, so please do check them out. We've supported over 20 early stage projects working in the space sector with our ongoing long-term Space Resources and Exploration Grant. So everyone building within the space sector is welcome to apply to that grant for a chance of receiving support from us. We've got a bigger initiative as well, which is our Starship Use Cases Hackathon, which has over $100,000 in prizes. Considering the vast potential of space exploration offered by Starship's lift capacity, we've developed over 20 use cases and open challenges for hackers or innovators to try their hand with. So make sure you have a look at the link in the description for that. You can get involved in that long-term hackathon or just apply for the grant if you're working in the field. So that's enough about us at DoraHacks. Today's topic, as I said, is applying NASA systems engineering to a space project. And I'm delighted to be joined by George Salazar, who was the human computer interface lead at NASA for over 40 years, if I'm correct. George, I'll let you introduce yourself in a bit more detail. The bullet points for today's workshop is number 1, complexity in human spaceflight missions. Number 2, understanding the importance of systems engineering. And number 3, the high-level description of the NASA systems engineering process. So it's going to be a fascinating workshop, I'm sure. I'll hand over to George now to go ahead with it. And if you're listening live, feel free to ask any questions in the comment section, and we'll have time for a Q&A at the end. So thanks for listening to me blurb all of that. And I'll hand over to you now, George.
All right. Thank you, James. And thank you, DoraHacks, for inviting me to speak to the audience. Just a little bit about a little background about myself. I was with NASA about 40 plus years before I retired, and I worked in various areas of spacecraft design, starting with the space shuttle, then space station, experimental X-38, experimental spacecraft. Most recently, fast forwarding here, I was working the Artemis program in the area of human ladder systems as well as Orion. And so I've had quite a few years of exposure to spacecraft design. And as part of that, I learned quite a bit about the systems engineering process and how vital it is. And so my talk this morning is associated with the systems engineering process. I have to say that this is a very abbreviated presentation related to the systems engineering process. I could probably spend all week talking about it. But be that as it may, I want to share a little bit of information, kind of give you a little flavor, if you will, of the systems engineering process, especially with complex systems. That's what NASA works with. I do have to say that the systems engineering process can be tailored to something lesser than a big complex project. It's up to the individual, though having experience in systems engineering gives you a better assessment of what you need and what you don't need. But my objective here is kind of give you a big picture view. So this is topics as James mentioned. I'm going to be talking about complexity of human spaceflight missions, and the complexity also transcends to unmanned missions, robotic missions. I'll say a little bit about that in my presentation. Understanding the importance of systems engineering and why we, at NASA, we use it, as well as other organizations that develop complex systems. Oil and gas industry, the railroad industry also uses systems engineering. So it's not unique to NASA. And then a high-level description of NASA systems engineering process as we apply it for human spaceflight, and to some extent for unmanned space flights, spacecrafts as well. And then just a few closing remarks. So the current major missions, and I'm not going to talk about all of them, but for the standpoint of the human space missions, we have the International Space Station ongoing right now. Right now, the plans are to retire it by the end of the decade. Be that as it may, right now it's been an incredible complex machine. First major let's say, spacecraft system that has ever been built in space and verified after it's been assembled. So it was quite a complex project. The Dragon system, I didn't mention this, but I also work commercial crew with the SpaceX in development of the displays for the Dragon system. Starliner, right now it's on station, and they're having a few problems with thrusters. But I worked actually also worked the human interfaces too for the Starliner. Axiom is a commercial company that's currently working with NASA to develop actually the commercial replacement, if you will, of a space station after we retire our space station. Now, from a human space missions, currently the big one is Artemis, and that's one I ended up doing the last 5 years of my career. It's ongoing right now. We have the Orion spacecraft. I worked that in terms of human interfaces, as well as a little bit of command and control. And then the space launch system. I didn't work that, but it's part of obviously the Orion spacecraft. It's the launcher system for launching the Orion spacecraft. And at the very end, the last 2.5 years, I worked in the lander system, working primarily with SpaceX and Blue Origin. Robotic space missions. Currently, Hubble is still out there doing great work in capturing pictures. And of course, more refined pictures is the James Webb's telescope. The IRIS, OSIRIS, is the one that returns samples from an asteroid. And right now at the Johnson Space Center, they're currently looking at the samples of that asteroid and seeing what the composition of it is. It was quite a successful mission. It was quite complex, to go out there several years, rendezvous with it, pick up some samples, and then bring it back to Earth. Solar Parkers, understanding and learning more about the sun, is the only human-made vehicle that's ever come close to the sun. Somewhere in the vicinity of, I think, 4 million miles from the sun. But it's been it's been a workhorse in terms of capturing data associated with the sun. And of course, right now, the Mars Perseverance robotic system on Mars, learning a little bit more about the Mars atmosphere, the Mars soil, and seeing if we can actually convert some of the atmosphere very weak atmosphere that Mars has into oxygen that astronauts could potentially use in the future. And of course, it's companioning the helicopter that recently was retired because of a broken propeller, Ingenuity. And Ingenuity was quite a remarkable feat of engineering using commercial parts along with radiation hardened parts. So it was an experiment in that, and actually that's going to transcend a lot of that technology into Dragonfly, which I'll mention later in my presentation. Yeah, and of course, the evolution of spacecraft complexity is quite remarkable. We started with the Mercury program, where you had just one astronaut in a spacecraft. They had about 55 switches to control the Mercury spacecraft. From that, we went to a two-person astronaut vehicle, Gemini. It was the first spacecraft with an onboard computer. Mercury did not have an onboard computer. All commands were sent from the ground. But Gemini, because of the nature of its mission to learn how to rendezvous and operate in the space environment for a longer period of time, required an onboard computer. So the complexity in human interfaces actually increased quite a bit, going to somewhere in the vicinity of 250 switches for controlling Gemini. And then, of course, the Apollo that took us back to the moon. And that one was really complex, despite the early technology, if you will, at the time. The command module had somewhere in the vicinity of 750 control switches for the command module. The lunar module equally had almost the same amount of switches, for controlling it. So it was a gradual and somewhat explosive. Actually, it was more of an explosive uh, uh, implementation of complexity of a spacecraft and the necessary controls needed for controlling such a complex spacecraft. And of course, the space shuttle, that's the one that I started with. Now, the space shuttle had really complex command and control system and human interfaces. That's just space shuttle had about 2,500 switches to control the space shuttle. But it was a remarkable machine for the technology at the time. It launched like a rocket, orbited the Earth like a spacecraft, and returned to Earth like a high-speed jet, if you will. So there was a lot of lessons learned about this, using space shuttle technology that carried over to space station. Space station came exceedingly complex, somewhere in the vicinity of 350,000 sensors. It had somewhere in the over 100 computers. There was a lot of command and control using laptop computers, actually. So it was quite complex. It was a quite complex machine. And I have to say that it's unfortunate they're going to have to retire it, but things are getting old, and as things get old, if you have an old car, you understand that you have to repair it quite frequently, and that's been happening with space stations. So that's why Axiom is going to take over and build a commercial spacecraft to still keep a presence in terms of space stations orbiting the Earth. In robotic missions, Europa, at the end of this year, they're going to send our orbiting spacecraft to Europa, one of the moons of Jupiter, and learn a little bit more about it. Interesting enough, it's got water and things of that sort that potentially could carry life. So that's going to be an interesting mission to watch. Lucy is going to be an orbiting spacecraft. Actually, it's going to be an approaching rendezvous with a asteroid later this year as well. That's the plan. Dragonfly, that's going to kind of leverage some of the let's say technology that the Mars helicopter used for basically landing and taking off of this helicopter on one of the moons of Saturn. So that's going to be an interesting mission to be carried out. And of course, Mars sample return is going to be an exceedingly complex mission. TBD, I said, for the date, because there's a lot of things that are still ongoing in trying to resolve the reduction in complexity and cost of that mission, which we're working with the European Space Agency in trying to return samples from Mars back here to Earth. So right now, hopefully the plan is somewhere around 2030, but we'll see. Interaction, development of complex systems is a function of n elements. The more people, the more things that you have interacting, the more complexity there is. Right there, I'm showing you somewhat of a representation of as you have more elements, and these elements could be spacecraft systems, people, or spacecraft systems and people. And so the more things that you have in a system, there's more interaction in terms of communications, in terms of interfaces. And of course, the interfaces are one of the, I have to say, one of the more riskier things associated with complex missions. And of course, Artemis, as I mentioned earlier, is the program ongoing right now. And that's in preparation going to Mars. And you talk about complexity, there's going to be a lot of complexity in this mission. Of course, we're going to have various international partners working us, to return to the moon, just like we did. You know, we went to the moon back in the Apollo era. Um, but we just went there to demonstrate that capability of landing on the moon. We only spent like a total of 3.5 days between the 6 missions that 12 humans walked on the moon. So it's not a whole lot of time. Now we're talking about, months and potentially years living and working on the moon to learn how to live on another planet as a dress rehearsal for eventually going to Mars, which is going to be much more challenging just simply because of the distance. Communications are going to be very challenging unless we come up with better technology, and we are working on that too as well. Looking at laser communications for high-speed communications between Earth and Mars. It's going to be a major challenge, and this is where systems engineering comes into play with complexity of this magnitude. And so you're going to have an increase in complexity as we progress in the mission from the early stages where we just land people on the moon, but then we started establishing an infrastructure down on the surface of the moon associated with habitats, in situ resource utilization, which is technology for basically taking soil from the moon and converting it to useful products for human, like for example water, as well as fuel for rockets. So it's just going to be a major undertaking, and also we're going to be building the first orbiting moon space station, and that's going to be new for NASA, along with its participating commercial partners such as SpaceX and Blue Origin, as well as international partners. And right now we have a whole bunch of international partners, including European Space Agency. If we even have Africa, we have, let's see, Scotland, we have Australia. I mean, just a whole slew of people that are going to be working to help us achieve the goal of preparation for Mars. Understanding the importance of the systems engineering process, it requires, what's it going to be used in the real world, the environment of what that system is going to be, or the mission in terms of what technology is going to be needed, and also the role of the human. You cannot overlook the role of the human. And that becomes important. If you look at this diagram right here, hopefully it's not too small, but basically you have to consider, as part of the design of a system and mission, is the hardware, the software, and the human in the environment and the mission, and all those have to be considered as part of the system design process. One thing that I've learned over the years is, hardware and software are somewhat deterministic when you design those components, but the human is not. Human is not very deterministic, and so you have to consider things and factor things when you're designing for the human, to think about how the human responds on a daily basis to controlling the complex spacecraft systems, and that's one of the challenges of human-computer interfaces, and that was the area that I worked. And then, complexity, it requires a tactical approach, a systematic approach. And, there you see a picture, I think it's, I forget the name of the automobile, but look at all the parts associated with that automobile, and they all have to come together in order to make that automobile operational. And so you think about a spacecraft, or you think about just about any major system, there's a lot of pieces that are associated with that spacecraft. And, you have to think about how you're going to decompose it into manageable pieces. And I'll mention more later in my presentation about that. But, you got to do formal analysis. And a key point is that when you decompose a system, it's a lot easier to basically design it, as opposed to trying to design it in a what they call a big bang approach, where everything comes together in one chunk and you're hoping for the best in terms of whether it's going to do its job or not. And here's another somewhat of a pictorial example of complexity and how decomposition makes things a little bit easier. So you got a complex system, but if you break it down to subsystems, the subsystem is a little bit more better understood. But if you break that subsystem down to components, it's even better understood. And now you can design something that's a little bit more manageable. And of course, all that has to come together collectively to basically represent the complex system. And of course, the complex system has a certain behavior that we're shooting for. So all the subsystem, the components, and everything collectively come together, to make that complex system operational and successful. So the importance of the systems engineering process is, and I said this previously, is methodically and discipline in terms of development of the system. You got many engineers working and scientists from different disciplines. I was on one project on space shuttle that we had about 250 engineers and technicians working on a particular project. Regarding or related to the space shuttle display systems. It's a rigorous approach to design, implementation, operation of system. And later I'll show a little high-level view of that through the systems engineering process. You got different teams developing different systems and different requirements. So you have to be cautious about miscommunications. And that's why, the complexity diagram I showed earlier about that interaction becomes important as part of developing a system, making sure that you're not overlooking something or you're missing something. And so the systems engineering process ensures to a high level that nothing gets missed. And sometimes we do, but for the most part, we do a pretty good job of developing complex systems. And so you go from a need of a goal of a system down there, you're looking at somewhat of a simplistic pictured block diagram. You're going from a goal, a need of the system, say, for example, going a moon lander, and the feasibility assessment. And that's part of the systems engineering process. Is it doable? Is it going to cost a lot? Or what kind of technology do we need? Does that technology exist? And then from there, we develop requirements, specifications. We look at the constraints. And then, through the systems engineering process, we churn all the aspects of, developing a system from the prototyping all the way to the actual flight system. And then, you assess that in terms of the mission and the systems that are needed, the hardware elements, the software elements. Where does the human come in? Is it are complex controls relegated to the hardware software, or is it the human that is going to be doing that? And so, human has certain limitations. We're not very fast in terms of computation. Obviously, the computer does a better job than that. But then again, the human is very good about being very creative and adaptive to situations and problems that occur, and the human can do quite a pretty good job of resolving issues given what he or she has available for trying to solve that problem. So it's a marriage, if you will, of machines and humans accomplishing a goal and accomplishing a mission. All right, and one of the things about systems engineering, as I found out over the years, is it's about managing risk. There's a lot of risk associated with a project, and here's a somewhat of a pictorial representation of what that looked like. You look at let's say an iceberg, and the top part of it, what you can see is what you expect the behavior and the technology and the human to be. This is this is what I expect the system to do. But underneath is even bigger piece of the iceberg, if you will, the risks that are lurking in program projects. You got safety risk. associated with your project. You got technical risk, you got cost risk, you got schedule risk, you got even contract risk. Interesting enough, there's a couple of projects I was involved with that the more of a challenge was dealing with the contracting of certain pieces of a particular system. So let me go now into a high-level description of the NASA systems engineering process. Excuse me, I'll take a gulp of water here. What you're seeing here is a systems engineering, sometimes they call it a systems engineering engine. And so it's somewhat of a V-shaped model, if you will. And you know, there's different V-shaped models out there, but they're all basically the same thing. You on the left-hand side of the V is definition design, and that's where you do, you know, stakeholder expectations. You're developing technical requirements associated with those stakeholder expectations. And then you're developing a logical decomposition. Basically, you're developing architectures, and you're looking at options. You're analyzing those options, and you come up with a design solution based on all your analysis that you came up with. And then on the right-hand side, you get into more of the implementation, where you start integrating the small pieces into the bigger pieces, subsystems to the systems. And you do verification. You know, did we build the system right? And then you do validation. Did we build the right system? And then you transition to the next phase. Like, for example, the Orion spacecraft, you transition that over to the Space Launch System, where they both are integrated for launching to the moon. And this process doesn't begin to until phase A. So here's somewhat of a quick picture of the program life cycles, and this is in the for those of you who's interested, it's on their website, MPR 7123.1D. It's basically the NASA Systems Engineering Procedural document. I'm proud to say that I have contributed to writing the update to that document. Our focus is human spaceflight, and that's what I highlighted right there. There's also a unmanned version of this, but that's the one that we focus on at the Johnson Space Center, especially because we know we got humans involved. And so if you look at the life cycle of it, you know, we have, you see up here, we have the life cycle phases where we do pre-formulation, formulation, and implementation. And so each one of these has a control gauge. They're called key decision points, KDPs, and I'll kind of go through them briefly later in my talk. But key decision points basically says, are you ready to the next phase? And you know, you certainly don't want to get approval for funding when you are not ready to go to the next phase. And so each one of these key decision points has a criteria and quite a few pieces, requirements, if you will, criteria for going from one key decision point to the next. But it's the only way to basically ensure that this system is being developed correctly, that problems that are occurring are addressed before going on to the next phase. You don't want to go into the next phase with a whole slew of problems without have not resolved problems that could impact you later during your development and implementation phase. So we go from an idea, approval of the formulation, to implementation, to the actual system, final system design. So pre-phase A is basically somewhat of a feasibility and assessment that I mentioned earlier in one of the block diagrams. And so the feasibility assessment, you're looking at many things. That is this going to be worth the money for the government or a commercial company or whoever is going to pay for it. You have to assess the costs. You address system level requirements. These aren't final requirements, but these are kind of like preliminary system level requirements to understand the scope of what it's going to take to develop this system. and identify potential technology needs. And so there you're scoping, you're looking at needs, objectives, you're looking at the mission, you're looking at constraints at the early phases. And certainly the constraints are going to increase as you progress along, but it's the first try at looking at that. Responsibilities, who's responsible for what? That actually becomes very important too as well, especially when we're working with multi-teams and you're making assumptions. Sometimes you don't have an answer, but you make assumptions, and the assumptions could be right, but at least or wrong. But at least you have a first cut of what you think is going to take to do this project. And here's something called the technology readiness level thermometer, if you will, and it basically and this is on the web too as well, and it is basically NASA's way of assessing the readiness of new technology. And it's not just for the new technology, but also down here at the bottom, you're looking at the human. What kind of technology is going to be needed to protect the human for a particular mission? And of course, the human body has a response to many things associated with space radiation, altered gravity, isolation confinement, that's more psychological than physiological, hostile close environment, how we're going to protect these astronauts, and then the distance from Earth, the things that they're going to affect them in terms of, let's say, medical care and things of that sort. How are we going to deal with that, and what's the technology needed for that? So the next phase, and those are actually the key ones that I highlighted right here. And basically, a PDR, and I'll mention this later, is the technology readiness level 6. That's basically a control gate too, as well as the maturity of technology as we're developing these systems. And if everything it looks good, and the reviews go well, and everybody's hunky dory with what's been presented, is they're going to go to phase A. And then I'm going to briefly just mention phase A, because phase A is basically, you're and I circled that in the systems engineering engine. You're doing the technical requirements, and that's kind of the bottom line for phase A. As a result, you go to what they call SRR, System Requirements Review. Have all the requirements been captured? Safety requirements, environmental requirements, all the requirements associated with the mission that this system is being designed for. Have you done order prototyping testing? What are your results? What are your concept of operations? And have you refined it? The concept of operations becomes critical later, especially when you're validating a system. And so here's kind of an example of some of the things that go on: prototyping, environmental testing. There you see at the bottom, thermal vacuum testing to kind of simulate the space environment requirements. And if everything is approved, then you go to key decision point B, approval for formulation, phase B. So things start getting a little bit more hairy, so to speak, and more refinement of the design. And there's a lot of things that go on, and I've just kind of mentioned here a few risk management updates, make or buy decisions in terms of the trade studies, because at this point you have come up with some trade studies, option A, option B, option C, but you try to refine it down to one option. And once you've refined it down to one option, you hold a preliminary design review and saying, we have decided to go with this point design, for the system. And there to the right, you see the phases in the definition and composition of the systems engineering engine associated with PDR, logical decomposition architectures, and these architectures are pretty much the option A, option B, option C architectures, and the design solution that you come up with. And then, here you're going from requirements to developing the behavior of the system, both the hardware and software, and to some extent the human. And then you're allocating all that behavior to structure components or the human as well. And so there's, again, an increase in complexity in terms of designing the system. but you're also doing environmental testing to see, hey, is this thing really going to work in the actual environment before we start pumping a lot of money into the actual flight system. And so we also evaluated in terms of the human capabilities in controlling the system, looking at human error analysis, human in the loop testing. It's called HITL, HITL. And you're assessing and you're improving and you're going back to the design solution. So preliminary design review is, it gets very busy in terms of work. But if everything comes out okay, and during the preliminary design review, everybody says, you're ready to go, then key decision point C occurs now. You can go to key decision point C because you've now shown that you're ready to really sharpen pencil and start designing the system more for the space environment. And of course, it gets very expensive in key decision point C because the testing gets very expensive. An example, radiation testing for just testing one board for heavy ions at Brookhaven runs about $65,000 for maybe a couple of days. So it's not cheap to do radiation testing. And then in phase C, you're refining a lot of things. You're sharpening the pencil. You're looking at failure modes and effects analysis, fabrication, assembly, integration, looking at the lower level subsystem critical design review. Sometimes you have a system level design review, but you also have below that system level design review, critical design reviews of the subsystems that make up that system. So there's a whole bunch of design reviews going on. But again, it's somewhat of a decomposition, as I mentioned earlier, of basically simplifying a complex system. You don't want to do it all in one big bang, as I mentioned earlier. And, once you're complete, you're holding CDR. And then, the CDR is, basically the very details of the software, the details of the hardware, the details of the structure. And then laying out the wiring harnesses. Right there you see a wiring harness for the space shuttle. The space shuttle had 330 miles of wire, so quite a bit of wiring on a complex system. All right, and of course you're looking at also the one of the these are tracking charts, related to a critical parameter, like for example, power, size, or weight. And it's a way of making sure that we're not going over a particular critical element that we're watching. I know early on the ride was too heavy, but the technical performance measures were reviewed at each interval of design reviews, and they were seeing that it was getting very heavy, and so they had to go back and say, okay, you guys, you're going to have to reduce the weight of this. And so technical performance parameters or measures such as power, weight, or whatever is monitored on a particular basis, and you have an upper margin and a lower margin that you have to stay within. And you're now good to go to key decision point D. And now you're going into where things get really expensive. You're doing crew training, and you're doing all kinds of integration, verification, validation testing. You're working with the crew with the actual high fidelity system. And this is all going to take you to flight readiness review. And this is a major review, 3-4 days, sometimes a week, sometimes as much as 2 weeks of reviews. But it's basically to flesh out or wring out any issues that could potentially come up when you're designing complex systems. There at the systems engineering engine, if you will, you're looking at verification, validation, and you also looking at mission control in developing how your mission is going to operate while your spacecraft launches to another world. So if everything is hunky dory, you go to key decision point E. All systems go. Get ready to launch the system. And here's an example. For example, the Artemis. Once the Artemis launches and all the elements are in place, you're going to have a major operational things going on. You got many teams overseeing the operation of the various systems. The orbiting moon station. You got the human lander system. You got the Orion spacecraft. You got the surface systems like habitats. And you're going to be monitoring this at Mission Control in Houston, as well as perhaps other mission controls throughout the country, including SpaceX and perhaps European Space Agency and other countries as well. Issues that come up, they're going to have to be resolved. I know that firsthand from my experience with commercial crew. We had issues with Dragon initially during some of the missions, but that's why you have mission control and mission support, to try to deal with those issues in real time and try to resolve them. There's going to be a lot of data acquired, and this is going to be distributed to the various stakeholders or parties of interest or principal investigators, and seeing where this, how this data is progressing in terms of its comparison to what you were expecting. And of course, the communications for that is going to be huge, especially when we start going to the moon, eventually to Mars. You think about an internet system that's going to have to be established with high speed, let's say, fiber optics communications to make this happen. There's going to be just incredible amount of data for this Artemis mission that is something that we have never done before. As I mentioned, we went to the moon in the Apollo, but we weren't there to stay. Now we're going to be there to stay, and so now we're talking about, an example would be instead of an orbiting space station, now we got, we have an orbiting, let's say, moon base, if you will. It's on the moon, and of course the moon orbits around the Earth. So we have a very complex infrastructure moon system that's going to be orbiting around the Earth that we have to monitor, not only on the moon with the assets that we have there, but also with the Earth assets in terms of mission control and all the support systems, antenna systems, ground systems that are going to be needed for this mission. And all this kind of boils down to the systems engineering process that I've kind of covered at a very high level, and I kind of reminded, and that's why I bring this chart up, is the human error associated with what's they call error analysis by James Reason. Did this in 1990. So what James Reason basically said that you have barriers associated with a system design. You have culture, the organization. You have requirements. You got design. You got safety. You got training. You got maintenance. But each one of these barriers to prevent problems have holes in them. We're not perfect, and holes occur. And then there's that period of time, and that's the reason I drew Swiss cheese somewhat in a circular fashion, because these things are revolving over time. But there's going to be a point where a hazard occurs and a particular barrier may or may not capture it. Here's an example of one that's deflected in the design. They caught it at the design phase. Or perhaps this one here that was caught at the requirements. It was a bad requirement for sake of argument. But then there's a case where all the holes line up for the different barriers, and that hazard results in an accident. If you think about some of the accidents that have happened over the years, airplane accidents, ocean-going vessel accidents. If you look at the accident report, you'll see that there are many things that were associated with why that accident happened. And I think James Reason pretty much hit it in terms of describing how that can occur based on this human error model or error model associated with barriers and associated with holes, if you will, that basically represent deficiencies in that barrier. People say, well, what about the culture and organization? Well, if your culture and organization basically does not consider safety reviews and safety testing as part of the development, well, that's a hole in the system. Okay, there should be that kind of reviews, and so, or if the project manager decides not to test a critical function, that's an organizational hole in the system. So each barrier spinning represents when a deficiency appears in time. And so it's just something to think about when you're designing a system or you're doing a hacking. Is look at look at the barriers to make sure that what you're developing is sound, and look at what holes are in there. And I have to say that systems engineering, a lot of it is associated with asking what if questions, and that's here's where you have a case where you if you have people that are pessimistic, actually it's good to have pessimistic people in your project, because they look at it from a what if this fails, what if that fails, and you have to listen to them, because it may be a credible concern, or maybe not, but if nothing else, at least you visit it, ensuring that it wasn't a hole in a barrier. So, in summary, future human spaceflight missions are going to be complex, no question about that, both including the system and the human. And, the NASA systems engineering process is critical for developing upcoming space missions, like, for example, Artemis, that's basically the proving ground that eventually will take us to Mars. And then the human is just important as the hardware and software. As I mentioned previously, hardware and software is deterministic. It's a little bit easier to design than designing for the human. The human, it's a little bit more challenging, and that's one of the things that you have to look at, especially when you do have human controlling complex spacecraft systems. And testing is expensive, but it's also vital to the program and project to reduce risk. If you're not testing, you're basically accepting the risk that this thing could fail in a certain situation. So something to think about. And I think that was my last slide. I'm going to stop sharing here and return over to control to James.
Thank you, George. Thanks, and thank you on behalf of everyone in the audience for that fantastic workshop and for taking the time to be with us today. So for anyone listening live, feel free to add your comments in the comment box, and I'll ask it to George. And we've got a few already from the community asked beforehand, so I'll just ask them to you now. If you just give me one moment.
Sure.
So how does systems engineering at NASA integrate feedback from astronauts and other end users into the development and refinement of spaceflight systems?
Yeah, good question. So part of the systems engineering process, and I mentioned this earlier, is stakeholder expectations and requirements development. So during requirements development, part of the group of people that are involved with that are actual astronauts that get involved, that have flown missions before, because they have real world experience in what worked, what didn't work, what they saw, what they didn't see in terms of deficiencies in the system. And so the systems engineering process ensures that we incorporate feedback from, not just the various stakeholders involved, safety people, mission operations people, but also the actual users. And in the case of NASA, the actual users are the astronauts for the spacecraft system, but we also have the users in mission control that are using the mission control systems and the ground operation systems for controlling a spacecraft. So the systems engineering process tries to ensure that everybody's input has been noted and heard.
Okay, great. Yeah, thank you for that. Another question, you may have touched on some of these in your workshop, but it is, can you share how NASA's systems engineering process has evolved over the years and what major improvements have been made?
Oh, very good question. So it's involved. It's been evolving. In fact, one of the things that I was involved with was adding a little bit of adding the human element into the systems engineering process. Prior to I think it was 2020, the systems engineering process pretty much talked about hardware and software for the most part. And so basically, I was part of the group that upgraded it to adding a little bit more of the human element in the development process, and also providing, let's say, a group that I worked with was adding a human systems integration handbook, if you will, of how you integrate the human into the systems engineering process. And it was a book to basically provide guidance in that aspect. The other part that has evolved, that's evolving to some extent, is model-based systems engineering. It's a little bit slower being accepted than what people had thought was going to occur, and I think it has to do with just simply because of how things were done previously. It's very hard to change a certain thinking pattern, if you will. And so model-based systems engineering is being used more and more. It was used quite a bit on the Orion. It's used more and more now on the Artemis program. And I have to say that because of the model-based systems engineering, the next step now in evolution in the systems engineering process is what we're calling the digital engineering. Okay, now you got basically models, and you got the use of digital twins. Not to say that NASA has not used digital twins in the past. We actually have to a very limited degree, even in the Apollo space program, but it's going to be more vital for the Artemis program, and more so because we're thinking about doing a digital twin for a human and monitoring how the human behaves with the models, human models that have been developed. So the whole thing about digital transformation is now becoming part of the NASA systems engineering process. So the evolution has, I have to say, is going from, let's say, paperwork, simplistic tools like Excel and PowerPoint to more complicated type digital transformation, model-based systems engineering, safety model engineering. I mean, there's a whole bunch of models that are starting to come up in terms of all this digital transformation that NASA obviously sees is going to be vital in order to making sure that we are successful in the implementation of the Artemis program.
Great, very interesting. One final question, which is just more a general one for the audience. What advice would you give to new engineers or students aspiring to work in systems engineering for space missions?
Okay, so systems engineering, of course, you can get a degree in systems engineering, and I did after doing systems engineering for 16 years. I have to say that you basically evolve as a systems engineer over time, and I have to say that my career, I started early doing systems engineering. I didn't know I was doing systems engineering at the time. But I got involved with requirements development, and I started to understand, what's a good requirement, what's a bad requirement, what do you have to consider when you're designing systems. And so this comes with experience. I mean, you can read about it, But until you start doing it, and the example I tell them is, let's say a carpenter. If you want to be a carpenter, if you read a whole book about how to do carpentry, uh, you may not do very good the first time you build a house. You actually start building a house is when you start learning what it really is, to build a house in carpentry. Same thing with systems engineering. There's a lot of things that, they're taught in the books that I learned. Yeah, yeah, I understand this, but in the real world, let's call them roadblocks that occur. And so, and I have to say that a lot of them are associated working with people. And that's something else that I learned is dealing with people is a major consideration as being a systems engineer, because you got to deal with different personalities. And you got smart people, but if they're hard to work with, it's a bit of a challenge. And negotiating, I was not taught as an engineer to negotiate. So you learn that by the seat of your pants, and of course, you can take classes on it. So I have to say, for the students, that want to be systems engineers, is to first learn the discipline that they're working on or pursuing very well, but then start evolving over time to consider systems engineering and start thinking classes in it, but also do hands-on systems engineering too as well. That's where you really start to learn.
Yeah, great. It's all about applying what you've learned as a student, I guess. Yeah. So thank you, George. That does actually lead me on nicely to reminding everyone that we do have two ongoing activities on the DoraHacks platform, one being the Starship Use Cases Hackathon. The submission portal is open now, and we've got a prize pool of over 100K USD. So if you're interested in the Starship, or just want to get involved, it's a creative themed hackathon. So check out the link in the comments and get involved in that with a team to get your hands on some of that prize pool. And then we also have the Space Resources and Exploration Grant Program. So if you're a student society or a group working in the space sector, then do check that out and consider putting through an application, because we love to support innovation in the space there. And keep in touch with DoraHacks on our YouTube and Twitter at DoraHacks, because we have more workshops coming up in the future, like this fantastic one from George Salazar today. So thank you so much, George, for joining us and sharing your knowledge with everyone. We really appreciate it.
My pleasure. Thank you for having me.
Okay, have a lovely day. Thanks, George. Bye-bye.
Thank you.